Welcome to day number 1 of related rates. This is a section that is among the most difficult in AP Calculus. And I think the reason that students struggle with it is because each problem is so different than other problems on the same assignment. But really, there are 6 steps that you can use, and I've listed them here. And if you take them in order, really your life will be a lot easier and things will go a lot more smoothly. First and foremost, you must make a goal statement. Without a goal statement, you really don't know what you're doing, literally. So once the goal statement is made, you'll draw a picture and label the parts. You'll come up with an equation, possibly a couple equations, usually from geometry. Pythagorean theorem is a frequent flyer. Obviously, so is SOHCAHTOA, your right triangle trig, special right triangles, some of the volume and surface area formulas from three-dimensional geometry are going to be in there as well. Once in a while, you even get a real tough problem where you'll have a law of sines or law of cosines thrown in there. Next up, you eliminate a variable if possible. Sometimes it simply won't be possible, and that's okay. And then finally, we actually get to do what we do, which is calculus. We take a derivative. And then finally, after the derivative is taken, we can plug in all the numbers that we know and solve for the variables. You have to wait until after you've taken a derivative to plug in any numbers. That's very important. That order has to be 5 and then 6. All right, the best way to learn this is just to go after it. So we're going to try a couple examples on day 1, and in day 2 we'll come back for the last 3 examples. So here we go. Number 1, a classic ladder sliding down the side of a building problem that every textbook seems to have. Okay, there's a 35-foot ladder. It's leaning against the side of a building, and the bottom of the ladder is being pulled away from the building at a rate of 2 feet per second. All right, I'm going to label some parts. We'll make a goal statement, and then we'll see what we have. All right, I'm going to assume a right angle right here, assuming that the building was properly constructed. And we need to label the sides. I'm going to call this piece here X because it's horizontal. The vertical I typically will try to label as Y. And the 35-foot ladder is simply 35 feet. That's not going to change as the ladder slides down the building. It's not like it's going to get longer or shorter. So we can keep the 35 there. We do not need a third variable. So that's great news. All right, it says that the bottom of the ladder is being pulled away from this side of the building at a rate of 2 feet per second. So in other words, imagine somebody right here at this red dot pulling sideways at a rate of 2 feet per second. Well, that's going to make the X side of this triangle grow. And so it's going to grow every second by 2 feet. So this 2 feet per second is actually dx dt. And similarly, the Y side, the vertical side of the triangle, is going to shrink until eventually it's 0 when the ladder crashes against the surface of the ground. And so this top piece right here, this yellow dot, if you will, is going to be moving down the side of the building. And we want to know, how fast is that happening? How fast is the top of the ladder sliding down the side of the building? And so in other words, that's like asking, how fast is side Y changing? So really, our goal statement needs to be find dy dt when the bottom of the ladder is 21 feet away, when X is 21. All right, let me write that down. Okay, goal statement made. We have the picture with the parts labeled. So those are our first 2 steps. The next step is to write an equation, usually from geometry. And obviously here we're going to use Pythagorean theorem. A squared plus b squared equals c squared, or in this case, x squared plus y squared equals 35 squared. Okay, the next step is to eliminate a variable if possible. Unfortunately, here it's not possible, so we forge ahead. We're ready to take a derivative. The derivative of x squared, of course, is 2x, but you have to remember that we're trying to find dy dt, and so we need to be in terms of time, or t, and we're not. That's x, not t. That's the wrong letter. So we need an implicit chain rule, dx dt. It's sort of like me admitting, yeah, I know, it's an x, it's supposed to be a t. And you're like, okay, you're cool. Carry on. All right, the derivative of y squared, bring down the plus sign here, is 2y, but of course that's also the incorrect letter, so we need a dy dt. Again, that's a form of a chain rule. It's implicit differentiation. And finally, 35 squared, I mean, yeah, it's 1225, but who cares? Because its derivative is going to be 0 anyway, which is why I decided not to bother squaring it out. And to keep my life as easy as possible, I'm also going to go ahead and divide both sides by 2. That'll knock these 2's out that I don't really need. 0 divided by 2, of course, is still 0, so it's all good. And now that I've taken a derivative, it's time to be able to plug things in. Now, I wasn't able to plug in the x's and the y's and dx dt, dy dt until now, but once I have taken the derivative, which has passed, thumbs up, green light, we can do it. Okay, well, I know that x is 21 because it says so in my goal statement, so I can plug that in right away. Let's go with some red. So x is 21. dx dt is 2, because that's also something I already know. The y I don't know, but I can figure out using Pythagorean theorem. And dy dt is what I'm trying to figure out. That's why it's nice to have the goal statement written down. So find dy dt. So I don't know what this is. I'll just copy it down. All right, we just need to figure out what y is. I will go ahead and start by looking at this right triangle that we have between the ladder, the building, and the ground. I'm going to go ahead and move it out of the way just so we can get a better look at it. Let's kind of drag it over here. There we go. We know that the ladder is 35 feet. That has not changed. That's not going to change. We know that the bottom of the ladder is 21 feet away from the building. We know that because of the problem and because of our goal statement. So we know that the x is 21. So I can fill that in as well. And then I can use Pythagorean theorem to get the y side. If you want to take a shortcut, I don't know if you realize that this is a 3, 4, 5 triple. And so y is going to end up being 28. When I made this problem up, I took the 3, 4, 5 and just multiplied all sides by 7. So we have 3 times 7, 4 times 7, 5 times 7. So getting the 28 that way is a huge time saver. And it saves you from having to grab a calculator or that sort of thing. Obviously, if you use the Pythagorean theorem, you're going to be able to get 28 just as easily. All right, so let's see what we have. 21 times 2, of course, is 42. And that's equal to 28 dy dt. Let's go ahead and rearrange this. I'm going to subtract 42 from both sides and then rewrite this. And dividing both sides by 28 will leave me with dy dt being negative 42 28ths. We'll go ahead and cancel the 28ths away. And so dy dt, which is how fast the y side's changing, which is how fast the top of the ladder is sliding down the side of the building, that's going to, let's see, we can divide them both by 14. That's going to be negative 3 halves, or negative 1.5. And of course, on these word problems, we always want to use units. In fact, a lot of times College Board will have a unit point. So it's negative 3 halves feet per second. And that'll be our answer to problem 1A. Okay, so we know how fast it's sliding down the building, but what about how fast the angle is changing? Part B wants to know how fast is the angle between the ladder and the ground changing. So in other words, we're talking this angle right here. We'll call it theta, because that's usually the Greek letter we like to use for angles. Of course, we have a right angle right here by the building. So how fast is theta changing at that moment? Okay, I relabeled this, and we need another goal statement. This time it's going to be find d theta dt. And again, at this moment, and the moment was the same as before, when x is 21. All right, got a goal statement. We have a drawing with the parts labeled. Now we need an equation from geometry. And this time, since we're talking angles, I'm going to use SOHCAHTOA. Now I've got my choice between sine, cosine, or tangent. The worst of the three in this particular problem would be tangent. Why on earth would I want to not use the 35, which is a number, which is the hypotenuse? So I'm going to use cosine, but sine would be okay as well. Cosine of theta, that's the ka from SOHCAHTOA, cosine of theta would be x over 35. All right. Keep in mind that x over 35 is actually 1/35 x, so that might be helpful. All right, eliminate a variable if possible. It's not, so we're going to go ahead and take the derivative of both sides. The derivative of cosine of theta is negative sine of theta, but you have to remember that theta is not t, it's the wrong letter. We want d theta dt, so we need a forgiveness parentheses, if you will, or a chain rule, implicit differentiation. So it's going to be negative sine of theta d theta dt. Now the right-hand side, again, if it's 1/35 x, the derivative of that would be 1/35. But remember, x is also the wrong letter. It needs to be t, so we have a dx dt. So 1/35 dx dt. Okay, now that the derivative has been taken, we are allowed to plug in items. Again, we know what dx dt is. We know that that is 2 because that's this 2 feet per second down here. So that's going to be nice. So 2 goes in there. That makes the right-hand side 2/35. We don't know what d theta dt is, because remember, that's what we're trying to find. So this d theta dt that I'm boxing up is going to stay a mystery. But we can figure out what negative sine of theta is, because we have a right triangle. Remember from part A, we dragged this green triangle out and kind of set it off to the side. And I had mentioned to you guys, I'm like, well, all right, the 35 is not going to change. That's the ladder. That doesn't grow or shrink. This is 21 feet because of the directions. And you may remember that this was 28. It was a 3, 4, 5 triple. So now, if the theta, again, is down here in the lower right corner, if we're looking for negative sine of theta, that's easy. It's going to be negative opposite over hypotenuse. And that's going to be 28 over 35. In fact, heck, I can reduce that on the fly. 28 over 35, if you divide them both by 7, will be negative 4/5. So that goes in there. D theta dt we don't know. And again, as I mentioned, the right-hand side is going to be 2/35. So we have everything that we need. We'll simply isolate the unknown, the d theta dt, by multiplying both sides by the reciprocal, negative 5/4. That allows us to cancel everything out, which is really kind of satisfying for me. So we have d theta dt equals, then we have more canceling over here on the right. 2 and 4, obviously, we can cut in half. And then the 5 and the 35 will become a 1 and a 7. So d theta dt is negative 1/14. And again, we need units, and that's going to be radians per second. I know it's per second because seconds are mentioned in the problem. Radians are dimensionless, and that's why you can always put radians in. The beautiful thing about radians are that radians times seconds would be seconds, feet times seconds would be foot seconds, and that's just strange sounding. So that's why we like to use radius. It keeps the dimensional analysis super nice. And so our answer is going to be d theta dt equals negative 1/14 radian per second. And that makes sense because that angle should be shrinking as the ladder falls and slides down the wall. All right, that's part B. And finally, we have one more thing to answer about this ladder coming down the wall. 1C wants to know how fast is the area of the triangle formed by the ladder, the wall, and the ground. In other words, this triangle right here, how fast is its area changing at that moment? All right. Well, we need a formula from geometry. We first need a goal statement, though, so we're going to find dA dt, A for area. And again, at this moment, we'll keep the when x equals 21 as part of the goal statement. Okay, the goal statement has been written. Let's once again label the parts of the triangle. So again, this was x down here. Along the building would be y. I think I'll use yellow so it shows up on the brick. That looks pretty nice. And then, of course, 35. We don't need the theta angle because that's not part of the area formula. Speaking of which, area of a triangle would be 1/2 base times height. In this case, it would be 1/2 x times y, or 1/2 xy. Okay, our next step would normally be to eliminate a variable. We have not been able to eliminate a variable at all in this ladder scenario. Don't worry, in future problems that will be something we're able to do, just not yet. So we move ahead to taking a derivative, and unfortunately, since we still have two variables here and they are multiplied together, we're going to need some product rule. Oh, yes, we are. So I'm going to call this 1/2 x the u, and then the y will be the v. And of course, as always, product rule will be u prime v plus uv prime. So let's see, u prime is going to be 1/2, but that's the wrong letter. So dx dt. Okay, so that's u prime, and v is simply y. Just write the y down. It's not dy dt. The y is just the v, just bringing it down. Okay, u prime v plus u, which is 1/2 x, so just bring that down, not taking a derivative of it. V prime, the derivative of y is 1, but whoop, wrong letter, dy dt. In all these related rate problems, the proper derivative is time. And you know how often time occurs in geometry formulas? Pretty much never. So you'll always have the wrong letter. You're always going to have these parentheses or chain rules at the end, which is why we learn implicit differentiation right before related rates. Okay, the derivative has been taken, so now it's time to plug things in. So starting over here, we've got dA dt, which we do not know. 1/2, that's never going to change. dx dt, it's been 2 forever, it still is. That's how fast the bottom of the ladder is being pulled away from the building. Y is 28. Remember that from parts A and B. That's the 3, 4, 5 triangle. Plus 1/2 x. X is still 21. That has not changed. And dy dt, we figured that already in an earlier part of the problem. Let me just go back and remember what that was. That was from part A. dy dt was negative 3/2 feet per second. So I can use that in part C, negative 3/2. So we'll just kind of write that in. All right, everything we need, we have. The 1/2 and the 2 will cancel out, so this first part will be 28. Oh boy, let's see. Minus, because we have a negative, 63/4. Now, if this is a free response problem, by the way, you can leave it unsimplified like this. Please don't do that on my tests or quizzes. Students of mine that are listening, I want you to simplify for me. Don't make me crazy. So let's go ahead and simplify. Just to make this a little bit easier, 28, I'm going to rewrite that as 27 4/4, because I know where this is headed. And 63/4, let's see, 4 times 15 is 60. That's going to be 15 3/4. So we'll just replace those. And now this is going to be a lot easier. So 27 minus 15, let's see, we're talking 12 1/4 will be the answer. And of course, we always need units, so I'm just going to write it up here, 12.25. And we want to know how the area is changing. How fast is the area of the triangle changing? And area is in square units, so it's not feet per second, it's square feet per second. And that's how fast the area of the triangle is changing. So we're gaining 12 1/4 square feet every second. Now, normally you have to go 3 decimal places, but here, because it's a pure 0.25, you don't need to put the 0 at the end. If you do, great, but it's completely optional. All right, enough about ladders sliding down buildings. Let's do something completely different, completely unrelated. Here we have a cone-shaped container, and it's being filled with water at a rate of 8 cubic centimeters per minute. Cubic because it's volume. Okay, so imagine the water is coming in. It's starting to fill this thing up. But it's not all the way full. If it had been all the way full, it'd be 15 centimeters high, as you can see from the picture. But we only want the height of the water to be 9 centimeters, so it's about 2/3 full. And we want to know how fast is the water level rising when the water level is 9 centimeters. So again, I'm going to call the radius r and the height h. All right, we obviously need a goal statement. How fast is the water level rising is dH dt. So find dH dt when h equals 9. All right, we have a drawing with parts labeled. We have a goal statement. Let's see if we can go ahead and make an equation from geometry. This 8 that's coming in is volume. It's obviously water is 3-dimensional. If you didn't realize it's volume, the cubic centimeters per minute should give that away. So that 8 is actually dV dt. I'm going to write that down. So dV dt is 8. Just in case we need that later, we'll have it written and we can find it. Okay. And we need an equation, as I mentioned. How about the equation for volume of a cone? Again, from geometry. The volume of a cone, the volume of anything pointy, as you may or may not remember, is a 1/3 in front of it. Cones are just a bunch of circles stacked on top of each other, and circles are pi r squareds for their radius. I'm sorry, for their area, I should say. And then h is the height of the cone. So volume of a cone is 1/3 pi r squared h. Now, by the way, College Board will give you that formula. They give you any 3-dimensional formulas, any 2-dimensional formulas like the area of a circle, pi r squared, you better know. And hopefully you know those. So anyway, that's good. All right. Eliminate a variable if possible. For the very first time, it is possible. And the way I know that is through geometry once again. I have the full-size cone with a radius of 6 and a height of 15. And then I have a not-so-full cone with a radius of r, see right here, and a height of h right here. Now, I basically just extracted that and made its own picture. Both of those cones have triangles in them. They have right triangles, right angles. And both of these triangles share this blue angle at the bottom here. So by the reflexive property and by angle-angle similarity, we can make proportions. And so I will. I'm going to say r over 6, which is half of the 12. Let me write this down. R over 6 is h over 15. Now, there's several different ways you can write this. I could have said r over h equals 6 over 15. But as long as you do it the right way and you cross multiply, you're going to get 15r equals 6h. Now I can simplify that even further. I'll go ahead and divide both sides by 3. So that's going to give us 5r equals 2h. And notice my goal statement says find dh dt when h is 9. There's just h's littered everywhere. I don't want r's. So I'm going to come down here to the equation I was working on. I'm going to divide both sides by 5. And that way I have something to substitute. Whenever I see the letter r, I'm going to replace it with a 2/5 h. And that way I can eliminate variables. And so when I recopy this equation down, the volume equation, 1/3 pi, I'll just simply call that pi over 3. R squared, and we're going to put the r in and square it, h, which I will write as h over 1. Okay, the r, again, was 2/5 h, or 2h over 5, so I'll put that in. If I square that, that middle portion becomes 4h squared over 25. Let's just rewrite everything. So let's see, 4h squared times another h times a pi is going to be 4 pi h cubed. Down below, we have a 3 times a 5 being squared, which is a 25. So 3 times 25, that's 75. And now we've eliminated the variable. We have just v equals, so we have all h's. And that's what we want. All right, time to take a derivative. Let's go, we'll do the derivative this time in green. The derivative of v will be dv dt, which, by the way, I know is 8. How do I know? Because I wrote it down earlier, that's why I do that. Okay, so we'll put the 8 in later. We're going to need some more room eventually too, so I'll clear out some space. It says h is 9, so I can use that. So let's see, we've got 4 pi. Nope, I have to take the derivative first. My goodness. Let's back this train up a bit. All right, keep in mind that we have a lot of constants here. All of this is simply just one big number, and that's the coefficient. And we multiply it by 3. The 3 is just going to cancel into the 75. So we'll have 4 pi over 25. That looks better, I think. H to the second, because remember we're going to go down by a degree, down by a power. Oh, but that's the wrong letter. It should be times, so we need a dh dt. Chain rule. We're going implicit here. All right, awesome. And keep in mind, again, dv dt was 8, so an 8 is going to come down here on the left-hand side. I am badly running out of room, so let me just create some space. All right, there's some space I can use. All right, as I said, the dv dt over here on the left-hand side is going to be 8. I'm going to write that as 8 over 1 since I have other fractions. And that's going to be equal to 4 pi over 25. H squared, remember h is 9, so that's going to be 81. And finally, dh dt, which I am trying to find. All right, I tend to be the person who makes mistakes at this juncture, so I'm going to multiply both sides by the reciprocal. I'm going to take my good sweet time. So over here on the left, I'm going to put the 25 up top. I'm going to put the 81 and the 4 pi on the bottom. I'm not going to multiply them together, however, because some canceling will occur between the 4 and the 8, so keep my life easy. I'll do the same thing on the right. I just like to write things out and cancel them. It feels good to me, but also I know I'm not going to goof up anything that way. Everything's all good. I've got the dh dt by itself, which is the thing I'm trying to find. Like I mentioned, the 4 and the 8 are going to cancel, so some light cancellation. And that's about it. So I have 25 times 2. We're looking at 50. over 81 pi. Notice that the pi is in the denominator. This is not 50/81st pi. You can't put it off on the side, otherwise it makes its way into the numerator. You're always that person whose answer is 9.5 times larger than it should be. If I'm talking to you, make your fraction bar extra long. Now we just simply need units. And since this is the height, or the water level rising, it's not going to be cubic or square centimeters, it's just regular centimeters per minute. Centimeters per minute. And that is the answer to number 2. And this concludes day number 1 of related rates. So hopefully it was a little easier than advertised. Again, the most important thing is you can't plug in numbers until after you've taken the derivative. All right, we'll see you next time for day number 2. Take care, everybody.